Hi, good morning everyone. This is Jagdish, Assistant Professor of EC Department, SNS College of Technology, Coimbatore. Today we are going to discuss about applications of network theorem in electric and electronic circuits. So this topic is coming under the Unit 2, Network Theorems and Source Transformation. Now let's get to the topic. So, what are the applications of network theorem? So, we know the network theorem is used to simplify any complex network into a simple network. So, that is the purpose of network theorem, and we have studied so many several network theorems in this unit. When it comes to the focusing on the application, the network theorem have been developed in such a way that it could analyze a circuit with any type of complexity. Some network theorems are superposition theorem, Thevenin's theorem, and Norton's theorem. So superposition theorem tells us that if a network comprises of more than one source, the resulting currents and voltage in the network can be determined by taking each source independently and superpositioning the results. This means that electromotive force, that is EMF, present in the circuit is equal to the total sum of voltage drop across any form of the circuit component. So this is actually a superposition. And when it comes to the application, the theorem does not apply to non-linear circuits. Only it is applicable for linear circuits. The requesting of linearity indicates that the superposition theorem is only applicable to determine voltage and current, but not power. Power dissipation is a non-linear function that does not algebraically add to an accurate total when only one source is considered at a time. The application of the superposition theorem requires two or more sources in the circuit. So next thing, the Thevenin theorem. It is basically gives the equivalent voltage source corresponding to an active network. If a linear active bilateral network is considered across one of its ports, then it can be replaced by an equivalent voltage source. The equivalent voltage source is called as Thevenin voltage source, that is called as VTH, and an equivalent series impedance or resistance, that is called as RTH. So you could see this is the left side of the image which shows it's a linear active bilateral network. When this kind of a complex network, when you're using the Thevenin theorem on this complex network, that can be simplified like this. So this is a simplified version of the complex network, which has only one voltage source, that is Thevenin voltage, and another one is a Thevenin resistance. So Thevenin theorem is used to analyze of power systems, and Thevenin theorem is used to source modeling and resistance measurement using the Wheatstone bridge. So these are all the applications of Thevenin theorem. Next thing is Norton theorem. Norton theorem is the dual of Thevenin theorem. That states that any linear active bilateral network considered across one of its port can be replaced by an equivalent current source, that is a Norton current source, and an equivalent shunt admittance, Norton admittance. Since the two sides are identical, they must be true for all conditions. If we compare the current through the port in each case under short circuit conditions and measure the input impedance of the network with a source removal and a short circuit current, short circuited and current source open circuited. Then I Norton equal to ISC. So Norton current is also called as short circuit current. So Y Norton, that is the admittance case. So Y Norton equal to Yin. So here in the left side of the image, we can see there is a linear two terminal network. So it's a complex network. It is considered as a complex network. And the right side of the network, which is a simplified version of this complex network, which has one current source parallel to resistance, which is actually defined by IN and Rn. So the specific applications of the network Norton theorem is in the replacement of large part of the network with simple circuit used in simplification of network in terms of current instead of voltage. It also helps to accomplish a maximum transfer or next one is the reciprocity theorem. The reciprocity theorems tell us that in a linear passive bilateral network, an excitation and the corresponding response may be interchanged. In a two-port network, if an excitation E of t at port 1 produces a certain response R of t at a port 2, Then if the same excitation E of t is applied instead of to port 2, then the same response R of t would occur at the other port 1. So that means we can interchange the ports. Even though if we can interchange the port, the current will not be varied. That's called as a reciprocity theorem. So specific applications are acoustics and optics. The reciprocity theorem aids in understanding wave propagation, while in heat transfer it helps in devising effect insulation or cooling strategies. This wide usability underpins the reciprocity theorem's crucial role in various scientific and engineering practice. The next thing is maximum power transfer theorem. The maximum power transfer theorem states that for maximum active power to be delivered to the load, load impedance must correspond to the conjugate of the source impedance. This is called the maximum power transfer theorem. So the maximum power transfer theorem can be implemented to the linear network, the network system, along with RLC and restrained linear sources as elements. Maximum power transfer theorem functions only when there is a variable load. If not, choose the least available internal source of impedance which waves in maximum current through the fixed load. Consequently, maximum power is expelled by load circuit. So, and the specific applications are large sound system are built around this process. So, maximum power transfer is generated in the circuit by making speakers resistance equivalent to the resistance of the amplifier. Once the speaker and amplifier have equal resistance, both are considered as harmonized. So, another application is the relationship between the starter motor and the battery of the car engine. Power applied to the starter will rely on the effectively resistance of the motor and the battery resistance. When that is equal, the transmitted to the kickstart to the engine. So, these are all the applications of the network theorem. Thank you.